Hi guys, so we're ready to start into section 7.3, the law of cosines. So I just want to bring us to a page in our page one of our notes from 7.2, and just refresh that. We looked at four distinct cases of an oblique triangle. So we looked at the first two and how we could solve those two cases with the law of sines. So now what our focus is going to be on is what is the law of cosines and how can we solve case 3 and 4, right? Where we have three sides known, or we have two sides of the angle between them are known, right? All right. So let me just switch to full screen here. So just as a reminder, right, we will use the law of cosines for these cases, right? We're going to use that for side angle side and side side side, right? So let me just state what the law of cosines is. So the law of cosine says the following. If triangle ABC has sides of lengths A, B, and C, opposite vertices A, B, and C, respectively, then the following is true, right? So what I want to list is over here, I'm going to actually list the law of cosines equations. And then each one of these, there's going to be three of them, are going to have what we call an alternate form. So, both of these will become useful at times. So the law of cosines, the first one is a squared equals b squared plus c squared minus 2bc times the cosine of angle A, right? And then we have b squared equals a squared plus c squared minus 2ac times the cosine of angle B. And then c squared equals a squared plus b squared minus 2ab times the cosine of c, right? And then each of these in alternate form. So basically just solving for the cosine of A, cosine of B, cosine of C, just trying to solve for that, right? So cosine of A would be equal to b squared plus c squared minus a squared all over 2bc. And then cosine of B is equal to a squared plus c squared minus b squared all over 2ac. And then lastly, cosine of C equals a squared plus b squared minus c squared all over 2ab. Right, so these are the equations known as the law of cosines. Right? So for time's sake, I won't go over the proof of these, but I did post a video on Carmen if you're interested to see that. So the proof of this is on Carmen of where these equations come from. Right. So then I typed here just some guidelines for solving an oblique triangle given side angle side. So if you're given that situation, these are just some recommendations. So the first one is to find the length of the side opposite of the known angle by using the law of cosines. And then we can use the law of sines to find another one of the angles. And then lastly, we can find the other angles find the missing angle now, just subtracting it from subtracting the known angles from 180 degrees. Right. And notice for number 2, it's saying to focus on the, if you use the law of sines, you use the shorter of the two given sides. Right. So that way we know that's going to be acute. Right. So example 1, we have solve triangle ABC with angle B being 61 degrees, side length C being 19, side A being 28. Find the measures of the unknown sides and angles to one decimal place. Right, so we're trying to solve the triangle. So let me just, kind of the generic thing that I like to do when solving a triangle. Right, it's just labeling what we're trying to find, and then what we know is B is 61 degrees, C is 19 degrees, A is 28. Oops, not 19 degrees. Sorry, C is just 19. Right, 19 units. We don't know the units, and it would be a side length. It wouldn't be degrees anyway, right? But A is 28. And we want to round the measures of the unknown side and angles to one decimal space, right? So if you want to draw maybe like just a quick picture of this, right, just like a generic triangle here, we got A, B, and C, right? So what we know is that this angle measurement is 61 degrees, and right across from B is little b. We don't know what that is. Right across from A is 28, and right across from C is C, which is 19. Oops. That's A, that's C. Right, so you can see how it's, side, angle, side, because that's what we have, right? We have a side, an angle, and then a side, right? That's what we're given in that order, right? So that's why we have this situation, side, angle, side. So, if you notice, if you try to use a law of sines, it's not going to work, because what we need is we would need to know one of the following. We would need to know, this measurement or this measurement in order to use the law of sines to find, one of those two missing things. Or, if I just change the color here, maybe to red, we would need to know, this guy or this guy in order to find, using law of sines to find one of those, right? So you can kind of see that law of sines won't work for this. So that's why we need the law of cosines. Right, so remember the first recommendation is to find the length of the side opposite the known angle by using the law of cosines, right? So in other words, we're trying to find B, right? So using the law of cosines, right, we're going to want to focus on this second equation here to solve for little b, right? So we have b squared equals, a squared plus c squared minus 2ac times the cosine of angle B, right? So we can just fill in what we know. So we'd have b squared equals, so a is 28, so 28 squared plus, and then 19 squared minus 2 times 28 times 19 times the cosine of angle B, which is 61 degrees, right? So then b, of course, would just be the square root of whatever whatever this equals. Right? So another thing that I want to show you in your calculator for this is knowing how to store an answer, right? Because one thing that's been known in the course, and I've said before, is using a rounded answer to get another answer. We could have some rounding error, and that definitely will come up here. So I'm going to show you how to what we call store value, right? So if you have a graphing calculator, or even some scientific calculators will do this also, is we can store values as a letter, right? So let me show you how to do that. So the first thing is I just want to solve for b, right? So this would be the square root of 28 squared plus 19 squared minus 2 times 28 times 19 times the cosine of 61 degrees. right? Hit enter. And let me just double check. I believe my mode is in degrees, but yep, it is. So just to double check, right? We should be in degrees here. So then if I want to take this answer and store it, I can hit this STO button, right? That stands for store. And then I can hit alpha, and then I can pick a letter. So I'm going to store as B, just because, this is side length B, just to kind of help me remember what's what. So now, anytime I use alpha B in my calculator, I'm going to get that stored value, that exact stored value that we used. So that's going to be a best practice here. Right, so let me just write down what we got. So this is approximately 25.1, and just a note that I stored this as capital B, right, in my calculator. So now I can use a law of sines to find, and we were asked to look for. In step 2 is the shorter of the two given sides, right? So maybe we should try to find C, right? Find this angle. So sine of C divided by 19 is going to equal, sine of 61 degrees divided by 25.1, right? Which we know that's little b, right? So sine of C is going to equal 19 times sine of 61 degrees divided by 25.1, right? So that means that C is going to equal, arc cosine of 19 sine of 61 degrees divided by 25.1, right? But remember, though, this value here is rounded. So when I put this in my calculator, I'm going to reference that capital B value, right? So we want to do second sine, and then we are doing 19 times sine of 61. And then divided by B. Right? So that rounds to be 41.5. So this is 41.5 degrees. Right? And little b, I didn't write this down, but we already found that to be 25.1. Right? So then the only missing thing is to find the measurement of angle A. Right, so the measurement of angle A is equal to 180 degrees minus 61 degrees plus 41.5 degrees, right? Which this should come out to be 77.5 degrees. Right? So I found all of the pieces of this right triangle. Right? All right, so we have another one to try. So it's a similar idea, except we're given angle A, side C, and side B, right? So we have angle A, B, and C, and side A, side B, and side C. Those are the parts we need. So angle A is 108 degrees. And then capital B, we don't know C, right? Little c is 23.1. Little b is 89.2. And we don't know little a. Right? So again, we need to find the missing side. So we'll do that using the law of cosines. Right? So that would be a squared equals b squared plus c squared minus 2bc times the cosine of angle A. And then, if I take the square root of both sides, that would be A equals the square root of B squared plus C squared minus 2BC times the cosine of A. Right? And again here, just to point out, it's typically, I'd have a plus or minus in front here. But side A represents a side link, so that can't be negative. So that's why we don't have the plus or minus in front. Right? So then A would equal the square root of, so we'd have 89.2 squared plus 23.1 squared. So just filling in these values that we know. 2 times 89.2 times 23.1 times cosine of 108 degrees. Right, so if you throw that in your calculator, A turns out to be 98.8. Right, and again, I'm going to store this as A in my calculator. Right, so let me just do that really quick. Alright, so let me just type this in. Right, so then I'll just store that as A. Right. So then now what we want to find is we want to go the angle across from the shortest side given, right, which was C. Right. So we can use the law of cosine. So sine of C divided by 23.1 equals, and I'm going to have to use A, right? Sine of 108 degrees divided by 98.8. Right? So sine of C equals 23.1 times sine of 108 degrees divided by 98.8. Right? So then C equals arc sine of 23.1 times sine of 108 degrees divided by 98.8. And again, what I'm thinking is here I'm just going to use capital A that I stored in my calculator, right, for that value. So when I enter this in my calculator, I do second sine of, and then we had 23.1, 23.1 times the sine of 108 degrees divided by alpha A. Right? So that gives me 12.8 if I round to the nearest tenth. Right? So C is 12.8 degrees. So then, of course, to find B, I would just take 180 degrees minus 108 degrees plus 12.8 degrees. And that gives me 59.2 degrees. Right. So then the next objective is what if we have a situation where 3 unknown sides are known. So guidelines for solving an oblique triangle giving 3 sides are given here. So the first thing we want to do is use the alternate forms for the law of cosines to find the largest angle. Angle opposite of the longest, which would be the angle of the opposite of the longest side. And then 2, we want to find the remaining 2 angles using the law of sines or cosines, right? And then lastly, we can find the last remaining angle, because knowing the fact that they all have to add up to 180 degrees, right? So example 3, right? right? What we know is that A is 62, B is 48, and C is 41, right? So this is the longest side. So I want to find A first, right, using the alternate form. So the alternate form for A would be cosine of A equals B squared plus C squared minus A squared all over 2BC, right? So plugging in what we know, well, and I can also just write this as A is going to be equal to arc cosine of B squared plus C squared minus A squared all over 2BC, right? So then now I can just plug in what I know. So we'd have 48 squared plus 41 squared minus 62 squared, all divided by 2 times B, which is 48, times C, which is 41. Right? So for this, this should come out to be approximately 87.9 degrees if we round to the nearest tenth. And again, I'm going to store this as A. Right? So, second cosine of 48 squared plus 41 squared, 41, minus 62 squared. All right, close my bracket and then divide it by, open up another parenthesis, 2 times 48 times 41. Right, so there we get the 87.9. So I'm going to store this. So hit stow as A, alpha A. Right, so then now I could find like angle B using the law of sines. So anytime I can use the law of sines, I would recommend it. It's a lot easier. Sine of A divided by 62 equals sine of B divided by 48, right? And I wrote down this A value, just, this is stored. If that confuses you, you could just write down the 87.9. But just know when you type that in your calculator, I would recommend using the A value, right? So sine of B is going to equal 48 times sine of 87.9 degrees all over 62. So then B is going to equal arc sine of 48 times sine of 87.9 degrees divided by 62. And again, when I'm doing this, make sure you plug in reference A in your calculator. Right? Remember, arc sine is just the inverse of sine. Right, so second sine of 48 times sine of A divided by 62 gives me about 50.7, right? So B is 50.7 degrees. And then, of course, C would be equal to 180 degrees minus 87.9 degrees plus 50.7 degrees, which that gives me 41.4 degrees. All right, so that's solved. Did all of that. All right, so example 4 is another one where we're given 3 sides and we're trying to find, solve this triangle, right? So I have A, B, C, A, B, C. A is 18, B is 32, and C is 10. Right, we want to find each of these. Right, so the very first thing is notice that B, this is the longest side. So I want to focus on finding angle B. Right, so using the alternate form, from the law of cosines, we'd have cosine of b equals a squared plus c squared minus b squared all over 2ac. So we would have cosine of b equals 18 squared plus 10 squared minus 32 squared all over 2 times 18 times 10, right? And so this, if you plug that in your calculator, is approximately negative 1.67, right? But we know that cosine of b should be in between negative 1 and 1. This is outside of that range, right? So therefore, there is no angle that fits that category, that fits those that information. So in other words, there's no such triangle that exists. Right? So no such triangle is possible that has these three length measurements. Right? And that's my red flag. If I get cosine of b equals a value that's not in between negative 1 and 1. Right? So now ready for objective 3. So we're looking at applications of the law of cosines. So I had to throw a baseball example in here. I probably have told you that baseball is a big part of my life and my kids' lives. So I guess it's a softball, but it's still similar to baseball. So a regulation fast-pitch softball diamond for high school competition is a square 60 feet on a side. The pitcher's mound is collinear with home plate and second base. Further, the distance from the back of home plate to the center of the pitcher's mound is 43 feet. To the nearest tenth of a foot. Whoops, and I misspelled that. That should be foot, not food. Find the distance between A, the pitcher's mound at first base, and then B, the pitcher's mound at second base. Right? We can see that's what we're finding. So here's like a diagram to help us. So let me draw this in red. So basically what we're trying to find the distance between the pitcher's mound and first base, right? This is first base. So I want to find this distance here, right, is what I want to find. And I'm going to call that little lowercase a, right? So that means this is angle A. And then I'll let this be angle B. So that means this is little b. And this be capital C, which means this is little c, right? So in other words, let A equal the distance between the pitcher's mound and first base. Right, so we could use the law of cosines here. And something important to note is this picture might be a little hard to see, but this angle B is not necessarily a right angle, right? We don't know that for sure, right? And actually, it turns out that it's not going to be. But from the picture, it looks like it might be a right angle, but we can't assume that unless we know that for sure, right? So B is not equal to 90 degrees. Right? That's important to note. However, this, like here, this since this is a square, these angles are 90 degrees, right? So like where home plate, where it meets at the vertices of the square, those are going to be 90 degrees. So another important word is collinear. So collinear, the definition of that is lying in the same straight line, right? So in other words, this home plate, second base, and pitcher's mound, this is collinear, so this forms a straight line, right? So that blue line is going to bisect this angle 90 degrees, right? So in other words, what that tells me is angle A is equal to 45 degrees, right? Because what we can know is that this cuts that angle in half, right? So then, I can use the law of cosines now, right? Because we have a squared equals b squared plus c squared minus 2bc times cosine of a, right, as the law of cosines. And I know what b and c is, and now I figured out what angle a was, right? So a would be equal to the square root of, so just plugging this in, b was 60 feet, so we'd have 60 squared plus, and then c is the 43 feet minus 2 times 60 times 43 times the cosine of 45 degrees. Right. If you plug that in your calculator, you'll get 42.4 feet, right, approximately. Right. So then part B, we want to find the pitcher's mound and second base, right? So in other words, if I draw this straight line back in, like here's my triangle. Right, I know this distance was that was 42.4 feet. Or wait. No, we know this distance is given, which is 43 feet. Right, I know that this is a right angle. So let me just fill in like what we had before. I called this angle A, I called this angle B, and this angle C. So let me call this angle D, right, just to add this in. So in other words, this distance, all of this, would be thought of as little c, right, because this is a capital C. So little c is going to be equal to dB plus BA, right? So in other words, this distance, which is dB, and then plus this distance, dA, is going to be the measurement of C, right? And we know that this, BA, is going to be equal to 43 feet, right? And also, just to point out, triangle ACD is a right triangle, right? So I know that because this is a right angle, right? So I know that this measurement is 45 degrees still, right? And I know that this is 60, and I'm trying to find the hypotenuse essentially, right? So what I could do is just use the law, like law, not the law of sines, but just just the trig function, sine, since it's a 90-degree angle, right triangle. We'd have sine of 45 degrees, right? So this angle here equals the opposite, which is 60 feet, divided by the hypotenuse, which we call little c. Right? So little c is going to be equal to 60 divided by sine of 45 degrees, right? So, we'd have to multiply both sides times c and then divide both sides by sine of 45 degrees. And then we get this. So c comes out to be approximately 84.853 feet, right? But we want to know what dB is, right? Which would be this measurement, 84.853 minus the 43 feet, right? Because we found this part from here to here. I just need to subtract that part off, right? Or I want that part, and I found the whole length. So this would be equal to 41.9 feet, right? So that would be that solution. Right? So then the last objective here, we want to use what's called Heron's formula to compute the area of a triangle, right? So if we know all three sides of a triangle, we can calculate the area by using this formula, right? So let me present that. So given a triangle, with sides of lengths A, B, and C, the area is given by, so area equals the square root of S times S minus A times S minus B times S minus C, where S is the semi perimeter, right? In other words, S equals 1/2 times A plus B plus C, right? It's half the perimeter of the triangle, right? So we can use this formula if we're given A, B, and C to find the area. So let's try an example. So we're asked to find the area of a triangle with side length A, 15.4 meters, B, 22.6 meters, and C, 26 meters, round to the nearest square meter, right? So first, I would start off by finding S. So S would be 1/2 times A plus B plus C, which this would equal 1/2 times 15.4 plus 22.6 plus 26, which this equals 32 meters. Right, if you plug that in your calculator. So then the area is equal to the square root of S, so 32, times S minus A, so 32 minus 15.4 times 32 minus 22.6, which is B, and then we'd have S minus C, which is 26. Right? So then if you plug that in your calculator, you'll get an approximate area of 173 square meters, right? We're asked to round to the nearest square meter, right? All right, so that's all I have for this section. So as always, make sure you let me know if you have questions.